Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle the first LeetCode problem ever born, two-sum. After that, we'll go over two actual variants of the original question that Meta asks. The second variant is quite a doozy, so the lovely Summer will be covering that one. Alright, let's read the problem statement. We're given an array of integers called nums and an integer target. So looking at our example here, here's our array of integers and our target of 10. We want to return the indices of the two numbers that add up to our target. Taking a look at our example, we quickly realize that 4 plus the 6 indeed equals our desired sum of 10. Therefore, we'll return a list of both indices 3 and 1. This is what we return in our function. And real quick, the problem statement tells us that we can return the answer in any order. This means we can return the 3, 1 as is, or 1, 3, it doesn't really matter which one you pick. On that note, there's two more things that the problem description graciously clarifies for us. One, we cannot use the same element twice, meaning we can't use the 5 two times to add up to our target of 10. In return, a list of 4, 4. 2, there can only be one solution. So if you examine our example list here, you'll notice there's not another pair of unique numbers other than the 4 and 6 that we found that add up to our target. Okay, we understand our goal now, but how do we even approach this? Well, our intuition tells us to try every single possibility. In other words, we can consider this 3 as the one of two numbers that will equal our target of 10, and try adding to it all the rest of these numbers. So we tried 3 and 4. What does that give us? Not 10, it gives us 7. So we move on to try adding 3 and 2. We get 5 though, still not right. Let's try the 6, that gives us 9. 5 gives us 8, and 1 gives us the 4. None of those worked, so we can now re-anchor our 3 to the value of the next index with a value of 4. And now we can repeat the logic to try adding the rest of the numbers to it in hopes of getting a sum of 10. We'd try adding the 2 to the 4, that gives us 6, that's not equal to 10, so we move on. Next up, we try the 6, which, as we saw before, when we add it to our complement number of 4, we indeed get the 10. We stop there and we return the indices. That's great and all, but how do we do this in code? Well, we kind of simulated the whole workflow to a T. We can use a nested for loop and anchor a pointer called I that starts off at index 0, and then have an inner for loop with pointer j that starts on the next index at index 1 to go through the rest of the elements, and on each iteration, we'll add the two numbers to see if we got the sum that we wanted. It's quite redundant at this point, so let's do it real fast. 3 plus 4 does not give us 10, so we increment j. 3 plus 2 is not 10, neither is 3 plus 6, 3 plus 5, or 3 plus 1. Once we've exhausted j, we'll do what we did before and re-anchor our pointer I by incrementing it to the next index and starting j on the index after that at index 2. We do it all over again. 4 and 2 is not 10, but 4 and 6 is. The issue is this whole workflow yields a time complexity of n squared. We know better than to use a nested for loop with I and j. We can definitely code this much more efficiently, and as it turns out, we can actually do this in big O-N. But how? To see the intuition, let's revisit our brute force solution and try to think about it in reverse from another perspective and try to iron out what we should do. For example's sake, let's hyperfocus on when we had our nested pointer j at index 3 with a value of 6. Let me ask you this. What were all the values we tried adding to this very 6 to see if we got a sum of 10? Well, it was all the values beforehand, right? And it's true. We started our outer for loop pointer I at index 0, where we tried 3 plus 6. And then at some point, we re-anchored the I at index 1 to try 4 plus 6. Here, yes, we did get our answer. Realistically, we stop our loop here. But to prove a point, if this was like a 1 or something, then I would have eventually been incremented to index 2, where we try 2 plus 6. What I'm trying to say is, We tried all the possibilities with a nested for loop with big O-N, when really all we needed to find was the complement number of the 4 here. And we can do that with a single if statement. How, you ask? Well, if only there was a data structure that allowed us to look back at all the numbers so far and check if a number exists or not in big O1 time complexity. Well, lucky for us, there is. It's called a hash set. We'll use it and we'll change it if necessary. But that's the general idea. If we needed to look back as efficiently as possible to see if we got a valid pair, then we'll think about this the other way around and we'll iterate left to right, and on each iteration we'll add the number to our set. In this very contrived example, if we had already iterated to index 3 in our singular for loop, we would have added the 3, 4, and the 2 into our set already. So let's just do that real quick. And just as a note, yes, we still have a pointer named j here, but you'll see in our optimized single for loop, we'll name it I just because that's convention. So on our current iteration here at index 3, since we have all the numbers we've seen so far sitting pretty in our hash set, we can now look up if we have a complement number of 4 or not. Real quick, how did we even know we needed a 4 to begin with? Well, it's some more math manipulation. On any current iteration, we can just minus the current number of 6, in this case, from the 10 to get 4. That's the complement number. Okay, so we reached into our bag of numbers we've seen so far. Indeed, we have the complement number 4. We have our answer. And having found both of the values, let's return their respective indices. We have the 3 that our pointer points to, and then we have 1, but wait 1 second, we can't reference value 4's index. We don't have a pointer there at all. What do we do? Well, inspecting our workflow, ideally we'd still like to check for the 4 in big O1 time complexity, but then also return its corresponding index of 1. What we can do then is change our data structure from a hash set to a hash map, where the key is still the complement number to retain our efficient big O1 lookup, but where the value would be the corresponding index. So for a value of 3, we'd add the 3 but also its index of 0. For a value of 4, when we encounter it, we add its index of 1 as well. And then when we see the 2, we'll also add its index of 2. Great. With this, we're set to return the index of 3 of our value 6, and also the index of our complement number 4. This is our answer, and this is what we return. Okay, that was quite a bit of explanation. Let's go over one last example to put all these ideas together. All right, here's our example. We have everything ready for us. How convenient. On the first iteration, I is at index 0, where we have a value of 9. The first thing we'll do is compute the complement number that we need. What's 17 minus 9? We need an 8. So let's check in our hash map of all the numbers we've seen so far. Do we have an 8? No, we don't. It's empty. And furthermore, looking at our vector, we literally haven't processed any numbers yet. This is the very first one. All right, that's okay. The last thing we'll do on any given iteration is we'll make sure we add the value of 9 into our hash map with its associated index of 0. So you have 9 and then the 0. By doing this will set us up for success in later iterations when we look back to find complement numbers. Okay, let's move on. On the next iteration, we increment I to index 1, where we have a value of 3. What's the complement number we need? Well, 17 minus 3 is 14. We can peek into our map here. Do we have a 14? No, we don't. We only have the single 9. We can verify that in our original vector of numbers as well. It's only the 9. As always, we'll insert this value of 3 as well as its associated index of 1 into our map. 3 as the key and then 1 as the index. You kind of get the idea. Let's move on. We have a 5. What's the other number we need in our valid pair? It would be 12. No, we've not seen a 12 number yet. As you can see, it's only the 9 and the 3. Let's add the 5 and its index into our data structure. 5, 2, great. We move on. With a value of 8, we need a complement number of 9. This makes us super happy because when we look up 9 as the key in our map, we find it. This means we have a valid pair. Let's return in a resulting list two things: the current index that we're on of 3, as well as the associated index of our complement number 9, which is 0. There you have it. This is our answer. This is what we return. The time complexity has greatly improved to big O(n) because all we needed was a single for loop, and our space complexity has grown to big O(n) since we pretty much have to store every single digit as key value pairs in our map data structure. Okay, let's code this up. Okay, so first off, what data structure did we decide on? It was a hash map. It has a number key and a number value for the complement to the index respectively. That's all we'll need to start iterating. We'll do so through every single number. What's the first thing we do in any given iteration? We need to compute the complement number. Let's write some syntactic sugar here. Target minus our current number that we're on yields our complement number. We'll immediately check if our map contains that very complement number. If it does, we've reached an answer. We can easily return two things: the current index we're on, as well as the index of the complement number. If not, then we'll add the current number as the key to our map and the index as the value. Like the problem said, we're guaranteed one solution, so we don't actually have to return anything here, but we'll just choose to return a dummy empty list, because otherwise the compiler will yell at me. Okay, that's the code, short and sweet. Let's get into the first variant. Okay, the first variant surprisingly makes the original LeetCode problem simpler. We're still given an array of integers called nums and an integer target, but we want to return true if there exists a pair of numbers that add up to our target. Otherwise, we'll return false. This is the main difference in the variant. Instead of returning the indices of a pair of numbers, we return a Boolean, true or false. Furthermore, please note there can be multiple solutions, multiple valid pairs, but we only need to return true if we found one. As for our approach, we'll reuse our optimal big O(n) time complexity solution from the previous problem. I won't repeat how we arrived at this solution because I already explained it. Let's look at an example and see what other logic may change. Okay, as you can see, we have our hash map ready of the complement number as the key and the index as the value. We're also given the nums and the target of 5. And just like before, we'll iterate left to right, and on each given iteration, we'll do two things. 1, check for a possible valid pair with the current number, and if it's not found, we move on to step 2, where we insert the encounter number into our hash map. Okay, so on the first iteration, we have a value of 2. Does the complement number of 5 minus 2 of the 3 exist in our hash data structure? No, it doesn't. Therefore, we don't have a valid pair. We don't have a 3 to add to the 2 to get the target of 5. Well, now, just like the OG problem, we want to store the 2 in our hash map because it might be a complement number as part of a valid pair later on. So, okay, we certainly want to store the 2 as a key, but here's my question to you. Do we need to store its index of 0 as the value? Well, unlike the original problem, there's no requirement here to return indices. Therefore, if we only need to store the number as the key of our hash data structure and not a associated value, then a hash map is not super appropriate. We'd rather use a hash set, thereby eliminating this second value. A set would be more efficient and consumes less space. Alright, so we favor the hash set and we add only the 2 to the set. Let's move on to the next iteration. We have a value of 1. We'll repeat our logic. Does a complement number of 4 exist in our hash set? Sadly, we do not. Before we end the iteration, we'll add the current number of 1 into our set. Moving on, I will now be incremented to index 2 with a value of 8. Have we seen a number yet of 5 minus 8 of negative 3? Yes, it's possible we need a negative number, because in this case, negative 3 plus the 8, our current number, would yield the desired target of 5. Looking at our set though, we do not have that number, therefore we'll do one last thing and insert the current number of 8 into the set. On to the next iteration. We now have a 3. Do we have a complement number of 2 at all? Well, if we peek into our set, this time, actually, we do. It's right here. This is fantastic. We can immediately return true as an optimization, meaning we don't have to loop through the rest of the elements, because remember, though there can be multiple valid pairs, we only need to return true if we found one. We did, so we return true. This is what we return. Overall, the time complexity is big O(n), since we're still doing a single for loop, and the space complexity is also big O(n) because of our set here. Fantastic. This one wasn't too bad. Let's see what code we have to change. Alright, so here's our new signature. Not much changes. It's really just the return type, which is now a Boolean. Next up, let's dive into our body implementation line by line and see what needs to be changed. On line 4, we didn't want to use a map. We opted for the set. It's only going to store complement numbers, no longer the index, so let's get rid of one int and rename this as appropriate, perhaps complements, since it'll hold all of our complement numbers. Next up, our for loop looks fine, but we don't really need the I pointer anymore. Let's go for a for range loop. That simplifies things. Now we don't need to access via a pointer anymore. We can just reference the number itself to get the complement number. On line 7, we see if we have a valid pair or not. We renamed our hash data structure, so let's do that. And in the case that it does contain a complement number, we have an answer. We can simplify things and just return true. Otherwise, we'll insert the current number into our set. Last thing we'll do is if we loop through the entire vector but didn't find a single valid pair, we'll return false. There were none. Fantastic. And that's all we need to change. That was easy, but that wasn't the hardest thing. The next variant, however, is an order of magnitude more difficult. I'll hand the torch to Summer for that. Good luck.
Hello, it's Summer. I'll be going over another variant that is the most complicated version of twosome that Meta could ask. Let's go ahead and read over the problem statement. So we're given an array of pairs called dominoes and an integer target. If you take a look at our example here, we can see there's one domino. This domino consists of two numbers, the 2 and the 1. Next to it, we have another domino, 9, 1. Yes, I know there can only be 6 spots on a domino in real life. However, as you can see in our requirements here, the number can go as high as 9. Okay, so what we want to do is we want to return the number of unique domino pairs, where the first number of each adds up to the target. And the second number of both pairs also adds up to the target. What does this mean? Well, let's go to our example. Let's take this domino here, 7, 6. How do we calculate what the complement domino is that we're looking for? Well, we can minus 7 from our target, and that's going to give us a value of 3. Then we can minus 6 from our target. That's going to give us a value of 4. Scanning all of our previous pairs, is there a 3, 4? Why, yes, there's one here, but there's also another one here. We need to count both of these towards our answer. And yes, both of these pairs are considered unique because despite having the same value, they are technically at different indices. The only thing that we aren't allowed to do is use the same pair with itself. So for example, if we had a 5, 5 domino, then to repeat myself, we would not be able to pair it with itself. But anyway, we have observed that the frequency of the domino itself does matter to us. And since it'll count towards our final answer, we'll definitely need to track this in a data structure of some sort. And surprise, surprise, it's a hash map, just like the original LeetCode problem. Okay, with these ideas in mind, let's go through a full walkthrough. We'll begin our for loop where we have our first domino here, 3, 4. And the first thing that we need to do is figure out what the complement domino is to make a valid pair. Well, if we have 3, 4, then we can go ahead and do some quick maths in order to get 7, 6. The question is, have we seen any of these 7, 6 dominoes yet? Well, no, we haven't. This is literally the first domino that we've encountered. There's no valid pair yet, and we can tell because our map has literally nothing in it. On that note, we need to start populating it with the dominoes that we have seen so far. We'll end this iteration by doing one last thing and adding this current domino into our hash map. But how do we do that? Well, if we want to add the 3, 4 domino to be uniquely identified in our map, then we could intuitively concatenate the two numbers together to get 34. We can multiply this 3 by 10 to get 30, thereby shifting the 3 from the units place to the tenths place. That way we can just add the 4 in order to get our desired 34. Fantastic. Just a note, multiplying by 10 may sound random, but this works because we're only given the digits 0 through 9. Now we need to figure out what the value of the map is reserved for. Recall earlier that we determined that the frequency of the domino matters in order to ensure we capture every domino pair. So far, we've only seen this once, so let's go ahead and increment the value to 1. Let's go ahead and move on to the next domino, 1, 9. The complement pair for this domino would be 9, 1. Taking a look at our input, there is indeed no 9, 1 domino, so we need to end this iteration and add our current domino into our hash map. This is the first time we've seen it, so the value will be 1. Here we have a domino of 3, 4. The complement for this is going to be 7, 6. But unfortunately for us, we have no 7, 6 dominoes, so no valid pairs. As always, we end by adding the current domino into our map, but in this case, it already exists. Since we're seeing it again, let's go ahead and increment the frequency to 2. On the next domino, we would need a complement domino of 8, 9 in order to reach our target 10. We check and we see that there's no 89 domino, so there's not going to be a valid pair in this case. Let's go ahead and end the iteration by adding 2, 1 into our map with a frequency of 1. We are now at the 9, 1 domino. Do we have a complement pair of 1, 9? Well, taking a look in our map, yes, we actually do. And we see that this has occurred exactly 1 time. Therefore, we found a valid pair. Let's go ahead and add this number to a count variable that we are going to go ahead and return called result. And don't forget to add the current domino into our map. On the next domino, it's the same as before, so we know that there's a complement pair that it can match with. We can see in our map that the 1, 9 domino has a frequency of 1, so let's go ahead and add this pair to our results. Lastly, we need to add this domino into our map, so let's increment this value to 2. Now we are at the 7, 6 domino. The complement for this would be 3, 4, and taking a look at our array, we have not only 1, but 2 valid dominoes that it can match with. We'll go ahead and add the frequency of 2 to our result, giving us a result of 4 so far. Lastly, we add the 7, 6 into our map. We are at the last domino this time, and we need a complement domino of 9, 1. Lucky for us, there's actually 2 9 1s. We can also look here in our map and see there's a frequency of 2. Let's go ahead and add that to our result. We'll increment the current domino that we're on, and we have finished this loop. We have won the game of dominoes. In total, we have found 6 unique pairs, and that's what we'll return. The time complexity is big O-N, and the space complexity is also big O-N. Let's code, people! Okay, so take a look at our signature here. It's changed. We now want to return an integer, and as parameters, we're given dominoes as well as the usual target. The implementation for this variant is different from the original LeetCode problem, so let's go ahead and delete everything. What's our data structure of choice? It's a hash map of 2 ints, the domino to the frequency. We'll also need our result variable, which will represent the number of unique domino pairs. Now, let's loop over all of our dominoes, and we'll need both of its spots. The problem description referred to them as A1 and A2. On each iteration, what do we do? Well, first we'll compute the complement domino that we need. Remember, we minus A1 from target in order to get B1, and we need to minus A2 from the target in order to get B2. Next, we have to multiply B1 by 10 plus B2 in order to get the complement domino key. Next, we'll look into our map. Does this complement domino exist? If it does, we'll add the number of times that we've seen it to our result. Either way, we'll add the current domino into our map. We'll do some quick maths in order to get the key. Then we'll insert it into our map with an incremented frequency. When we're done with the loop, we'll return our result. And that's it. Bye!